Greetings, fellow learners. In this video, we are going to talk about the backpropagation by hand for a convolution neural network. So hopefully we're going to learn a lot. Now, let's start with a bit of a preamble as to what is backpropagation, why we need it, and then walk through our convolution neural network and then get into the grubby details. So first of all, backpropagation is an efficient learning procedure to compute the gradient vector of a loss function for a neural network. And this is in turn used to update the parameters of the network. So when we talk about the gradient vector, we're talking about this nabla L term here, which is composed of a bunch of individual gradient scalars. So for example, for like parameter P1, this term here gives how it does a loss change when changing the parameter P1 just by a little bit. Similarly for these other terms here. Now, while each of these is a scalar value, the overall vector, when evaluated at a specific parameter vector P, is going to give us the direction that corresponds to the direction of steepest ascent of this function L. Now, L is a loss function, and we want to minimize this cost. So knowing this direction of steepest ascent will actually help us in upgrading or updating each of these parameter values P. But computing this gradient vector is difficult when the number of parameters scales, as is in the case of like neural networks in general, and especially in the case of like convolution neural networks. And hence we use more efficient strategies to update these parameters, like backpropagation, in order to compute gradients and hence update parameters efficiently. So hope that's clear of what is backpropagation and why we would need it. Now, for our current neural network, we are going to work with one of these Linnet-looking architectures. So this is kind of an architecture devised in like from 1989 to 1998. There was a series of architectures from like Linnet 1 to Linnet 5 where it has like an input image, and there's a series of convolution layers, activation layers, some pooling layers, which is subsampling here. Then we also have some fully connected layers. And then we also have like classification outputs here that, we'll deal with like softmax activations. And so if we were to write this out, we're going to take like a very simplified version of this. And our network for today is going to look like this, where we have an input layer that's I over here. You can think of each of these representing like pixels as being on or off, 1 or 0. Then we have these like feature maps over here represented by like W1 and W12. Then we have the output of like convolving, these feature maps onto this image and sliding it over the image. We are going to get the results of these, the output of that convolution operation is going to be this layer over here that we've just denoted by C. Then we can pool these values to get these output neurons here. We just call it P, the layer. Then we have a weight layer followed by, the fully connected layer with ReLU activation, which we represent by H since it's a hidden layer. Then we have another weights layer followed by an output softmax activation here, which, assuming a calibrated model, would give us the probability of being of like one class or probability of being of another class. So this is kind of our network at a very high level. Now, once we get these probability values, we can then pipe it into a cross-entropy loss function in order to calculate the loss over here for a classification network. Now, in order to do this loss is a function of the predicted values of each class as well as the labels. That is, which class this actually belonged to, the input sample actually belonged to. Now, each of these neurons is kind of like a interconnection of neurons along with some activation function. And for the sake of trying to calculate the backpropagation and gradients by hand, we are going to split, the activation from just these individual neurons out across this network. And when we do this, we're going to get an expanded network. That's going to look something like this, right? So we have the input layer as normal. Then we have the feature maps over here We perform convolutions to get the output C layer here. Then we can perform an activation on these in order to get these sets of neurons here. To distinguish these layers from each other, I called the pre-activation. I labeled it with a superscript pre. Then we can pool these post-activation neurons in order to get these neurons here in P. And similarly, we split out the hidden layer neuron from its activation, which is ReLU, that this is pre-activation. Then we apply the ReLU activation to get this neuron, which is just H as the hidden layer. And then we're going to get like the sum of products. We just call this O as output. And we're going to perform a softmax to eventually get the prediction, right? And this prediction, along with the actual label, is going to be passed into our cross entropy loss function to get a loss value. And we'll be pasting this network up here on the screen for the duration of the video as we're computing the gradients by hand. And we'll just do some like mathematics fun stuff over here. So let's get to that. So at a high level now, when we pass an input to this network, we're going to get like activation values across, and then we will be able to compute a loss. And then at the backward pass, what we want to do is we want to compute the gradients of specifically the weight parameter vectors. That is going to be these values. It's going to be these weights and the weights over here too. And knowing these values, we can then compute that nabla L and use this gradient parameter in order to update each of these parameters here. So to do this, we start with this last neuron over here, and we want to determine basically how does changing this output affect this loss. That's quantified by this partial of L by partial of Y pred 1 over here to indicate this first neuron. We then do that. We then try to compute, how does changing this neuron affect the output? That's partial of L by Y pred 2. And then using these previous partials that we determined, the previous gradients, we can determine the gradient of like this neuron and how it changes this loss. Similarly for this neuron as well. And we can compute these gradients for every single neuron and eventually also like every single weight in the network. That is like, how does changing this weight affect this loss? How does changing this weight affect the loss? And so on. We can kind of work backwards in the network. And, we would use like the gradients that we compute along the way in its computation until eventually we can get to the beginning of the network. We can eventually compute the loss with respect to every single weight parameter in the network. And once all the gradients are updated, we can update all the weights with this gradient descent formula. So we've computed this. We will assume the learning rate as like, let's say 1 for this case, and we can update the weights, right? And all of this weight updates, if we do them at the same time, they should be in the direction of steepest ascent, but we're negative over here, so it should be in the direction of steepest descent. And so collectively, updating this weights in this way will work in minimizing the loss. Now that we understood this at a high level, let's actually get into the details. So let's say that we pass into the network the image of an A. So you can see that pixelated, it looks like an A here. The ones represent the on pixels for an A. We then pass it into this network, and we are then going to apply a convolution operation with respect to these parameters or these like feature maps over here. Performing a convolution, we will get this output here. Now, specifically, we can just see like how did we compute, this computation here is specifically just for this neuron right over here. So how do we compute this output here? Well, it's going to be taking this feature map and putting it right here on these top 3 cross 3 neurons, then taking a sum of products. So it's like 1 times negative 0.2 plus 1 times 0.2 plus 1 times 0.2 plus 1 times 0.2 plus 0 times 0.2 plus 0 times negative 0.2 plus 1 times this plus 1 times this plus 1 times this. And that's how you get 0.6. And that's exactly the computation that we see over here. This is an example. And similarly here, what we see is like 1 for the second where this entire, working out is exactly how we compute the value of this neuron over here. So it's using this feature map and applying this as a sliding window on this image, and specifically it'll be on this first 3x3 section. So doing that sum of products, we're going to get 1.5. And in order to compute like the second, again, like this, let's say this value over here, this feature map would be over here, right? In this like second region. Sum of products, you take it, you convolve it, and you get 0.4. And similarly, if you perform the convolution operation in this way, you can determine all of these values. Now, something I didn't mention before, but I will mention now, I'll highly encourage you to take like a pen and paper and actually work this out yourself. The computations on screen, I guess they're like nice for me to put together, but you'll really only understand this if you are doing this on your own and you can truly like digest this content and it's not just going too fast and over your head. So just a tidbit, some advice, but knowing that, hopefully you can kind of verify some calculations and understand the general direction how this works with this video. So moving forward. Now, from here we encounter a ReLU. So what we're trying to do now is we want to compute each of the neurons in this like C layers, right? So a ReLU activation is essentially going to be, it's going to be the same value that's passed in if that value is greater than 0. Otherwise, it's 0 itself. So it's always going to be floored at 0. So if you take, like, for example, 0.6, it's already greater than 0, so it's passed through as 0.6. 0.4, already greater than 0, so passed through. 0.2, it's passed through. 0.2, it's passed through. All the way until this last neuron here. Here, this is negative 0.2. It's less than 0. And applying the ReLU activation here, we are going to just get 0 as the activation. And similarly, we can do this also the second feature map here. And we can see the corresponding values over here. Next, we encounter a pooling layer. When we encounter a pooling layer, this is specifically going to be a max pooling. So it's going to aggregate and take all of the corresponding values of this output here, and it's going to just determine the maximum value. So what that is in this case is going to be 0.6 because this here and this are 0.6 tied for first. And this output is also going to be 1.5 because 1.5 is the maximum in this entire chunk of cells here. Next, we're going to perform a sum of products of weights and the input neurons. This is just like a feed forward layer, and we're just like passing in these values. So for example, this neuron here is going to be the sum of products of this weight and its neuron plus this weight and its neuron. And that's exactly what we see right over here mathematically. And doing the math, you'll get negative 0.18 over here. Similarly, you do it for the second neuron, you're going to get 0.18. And third neuron, it's going to be negative 0.42, as we see over here. Next, we encounter another ReLU activation, and when we do, that means all the negative values now become 0 and the positive values are passed through. Negative value 0, positive pass through, right? And next, we're going to now compute the output, which is again another sum of products layer, right? So doing the mathematics, you'll see that the sum of products of, to get this neuron right over here, it's this weight plus this neuron plus this weight times this neuron plus this weight times this neuron. The computation becomes pretty simple here because, the inputs are 0. So it's just going to be negative 0.5 times 0.18, which is negative 0.09. And hence we write it over here. Similarly for this second neuron, which is positive 0.09 if you do the math. Next, we compute a softmax activation. So this involves taking e to the power of like this first output divided by e to the power of this first output plus e to the power of the second output. Doing the math, you're going to get 0.45512. That's exactly what we see here. Similarly, for computing this second neuron here, it's going to be e to the power of this neuron plus, the sum of e to the power of these neurons together, which you're going to get 0.544, which is exactly what you see here. Next, we're actually going to compute a cross entropy loss, right? And the cross entropy loss formulation is going to look like this. So let's assume that, y1, the input here is going to be A, right? And A, let's say, belongs to class number 1, right? So that means y1, the label for it is 1, and y2, the label is going to be 0. And the loss function is going to be negative y1 times log of the prediction minus negative y2 times log of that prediction. So that's 1 times log of 0.455 minus 0, which is 0.787, which is exactly what we write over here. And this completes the forward pass for this single example. So I hope all of this makes sense. Now, in order to compute the gradients, which is the backward pass of this backpropagation algorithm, I thought some useful math would be right here. So for example, the derivative of e to the power of x with respect to x is just the same thing, e to the power of x. Derivative of log x with respect to x is going to be 1 over x. The derivative of a function, one function divided by the other, f over g, is going to be g of x times the derivative of f of x minus f of x times the derivative of g of x, divided by g of x whole squared. And probably the most important mathematical function here is going to be the multivariate chain rule. So let's say x and y are functions of some variable t, and z is a function of x and y. Then we can say that the change of z with respect to t is going to be the sum of changes through x, that's given over here, and y, which is given over here. So this is the multivariate chain rule that we will heavily use in the backward pass during our backpropagation algorithm, and you'll see how shortly. So in the backward pass, let's now start all the way over here, right? And now we start with this neuron here. How does changing this neuron slightly nudge the loss? How much does the loss change? So that's exactly represented by this gradient del L by delta y pred 1 in this case, right? Now we know the loss is going to be that cross entropy loss. And if we take the derivative with respect to the first neuron prediction, you know that's going to be, minus y1, which is constant with respect to this, times log of the prediction. If you take a derivative, it's 1 over that prediction value, right? Just like we saw in the rules, minus this entire thing is a constant with respect to y pred 1, so it's 0. And substituting the values, you're going to get negative 2.19722. So in English, what this abstract math is saying is that if you increase or nudge this y pred parameter by a very small value, like a 1 notch, then it will decrease the loss by 2.197 notches. And you can kind of verify that by just taking some values and just playing and actually changing them. So for example, with the current set of values, this is the current prediction, we're going to get the current loss that we just computed, 0.787194. Now, if you just increase this loss by 0.001, and then you just apply the forward pass at this point and compute the loss, you're going to get this value, 0.784999. And this will be the difference between these two. It's going to have decreased by 0.002195. So this means that if you increase this y pred 1 by 1 notch, you're going to decrease the loss by 2.19 notches. So it kind of is a good verification just for gut checking this abstract mathematics, just to show that you've kind of done this right. And we'll also represent that gradient of del L by del y pred 1 by a little delta above the neuron here. And I'm going to keep writing this delta over all the neurons throughout this network. Now let's consider the second neuron over here. So if we change this neuron by just a little bit, how much is the loss affected? That is given by this gradient operation over here, del L by del y pred 2. So we take our loss, take the derivative with respect to y pred 2, and in this case, this is going to be 0, and this is going to be negative y2 times 1 over y pred 2, since that's the derivative of the log value. And substituting the values, it's 0. So that means that if you increase this value by even a little bit, the loss remains unaffected. And you can kind of verify this by, just playing around with these values. Try to actually increase this value and see how much it changes. That's exactly what we did in this table here, and you can see that we've verified it correctly. And so I've added delta here is 0, so that's going to be the gradient value for this neuron. Next, we are going to compute the gradient of this neuron. So how much does changing this neuron affect the loss? Well, it can be computed along two paths. It's the sum of along this path as well as the second path here. So it's how this neuron affects this neuron times how this neuron affects this loss. That's represented by this first equation here, plus how this neuron affects this neuron times how this neuron affects this loss. That's represented by this equation over here. Now, you can already see that we've already computed these two terms here. We already know how these neurons here affect this loss. But what we need to compute now is how this neuron affects each of these neurons here. And that's these two terms. So let's compute those. Now, we know that this here is going to be like the soft max, right? So that's e to the power of O1 divided by e to the power of O1 plus e to the power of O2. And if we want to take the derivative with respect to O1, we know that this is like that f of x divided by g of x formulation. So it's the derivative of f of x, derivative of this, that's going to be the same thing, times g of x, which is exactly this, minus the derivative of g of x with respect to O1 is just e to the power of O1, times f of x, which is e to the power of O1. And if you kind of like look at these terms, they're going to be the same as like y pred 1 itself, and we can just write it in that way. And so we can see that this value just becomes 0.25. And if we were to compute it for like, how this affects the second neuron, it's also going to be negative 0.25. That means that if you nudge this neuron by like 1 notch, it's going to increase this by a quarter notch and decrease this by a quarter notch. That's kind of the interpretation. And so if you substitute those values in our multivariate chain rule, you can kind of compute that how does the loss affected by this neuron specifically is negative 0.5448. This means increasing O1, this neuron, by 1 notch will decrease the loss by 0.54 notches, which you can also verify by kind of just like plugging in these values too. Now, again, for this second neuron, we also, in order to understand how much this second neuron affects the loss, well, it is how much the second neuron affects this neuron times how this neuron affects the loss plus how this second neuron affects this other neuron times how this neuron affects the loss. That's given by this formulation. And doing the computation in almost the exact same way as we had seen before, you're going to like do the mathematics. That's going to look like this. Again, you're going to get values negative 0.25 and positive 0.25. And substituting those values, you're going to get a positive 0.54488. So that means that increasing this by like 1 notch is going to decrease the loss, or is going to increase the loss by also 0.54 notches. And that's given by this delta over here, this gradient here. So we've written both of the gradients for each of the neurons here. So I hope all of that makes sense. Next, we're going to compute the gradient of these weight parameters. That is, how is this changing this weight going to affect the loss itself? And how is this weight going to change the effects of this loss? So how does this weight change the loss is represented by this first value right over here. And it is, it can be broken down as how this weight affects this first neuron here times how this O neuron affects the loss. And that product is given right over here, right? These product of two gradients. And we've already computed, well, we know how this neuron affects the loss. That's just given by this delta value. And how this weight affects this neuron, since it's just going to be a sum of products, right? It's literally just going to be this input, 0. So that's going to be 0 times this delta value, which is 0 here. And so when we make that computation, we are just going to store it now in a table. And I'm choosing to store this in a table here rather than just write it on, on this entire graph for the weights specifically, because we will use these weights later. And so I'm going to store 0 right at this first position here. Now for 1, 2, that's this weight over here. It's the gradient. That's how does this weight affect the loss? It's how this weight affects this specific output neuron times how this neuron affects the loss. We already have that latter value. We already computed as 0.5448. And the form of value is just how this weight affects this neuron is just, the value of this input, which is again 0. And we write it in our table here. Similarly, how does this weight affect the loss over here? Well, it's the effects of the weight on this neuron times the effect of the neuron on the loss. We have that latter value, negative 0.5448, which you wrote over here, and then we'll multiply it by the input value, which is 0.18. And hence we get this negative 0.098 value, which we write over here. Now for this 2, 2 right over here, weight, right? How does this affect the loss? Well, it's how this weight affects this neuron times how this neuron affects the loss. And the latter value is 0.5448, and the former value is going to be 0.18. Hence, we computed the value here and store it in the table. And similarly, the other two, that is this and this, they're coming from a 0 neuron, so you can kind of like already infer that they will be 0. And I've done the math here just to show how they are 0, and we just write it here in the table. So hope that makes sense. Next, let's move on to this hidden layer H right over here, right? So how is this neuron affecting the loss? Well, it's how this neuron affects this neuron times how this neuron affects the loss, plus how this neuron affects this second neuron in the output layer times how that neuron affects the loss. That's exactly given by this multivariate chain rule formulation right over here, which we can substitute our values in, and we will get 0, right? Similarly, how does this neuron affect the loss? It can go in two paths, the same paths, that's either here or through this. And you can see that it's the sum of these two effects, which will be 0.5448. And for this third case, it's going to just be 0. And we've written their corresponding gradients right on top of each neuron. Next, we encounter a ReLU activation, right? So ReLU, we already know what it looks like in the forward pass. It's just going to, floor values that are under 0 to 0 and just pass through values above 0 as is. So what we want to calculate now is how does this neuron affect this loss, right? So it's how changing this neuron affects this neuron here times how changing this neuron affects the loss. That's exactly what's given by this formulation right here in chain rule. Right now, we already have one of these values. We already have this, this value right over here, right? Now we just need to calculate the second term, right? How does this neuron affect this neuron right over here? If it's a negative value and you change it by a little bit, it's not going to change the output at all. But if it's a positive value and you change it by a little bit, it's going to have the same exact change on the output. So that's like a 1-to-1 ratio. And that's why we get the derivative that looks mathematically represented like this. Or, we can also say that this is purely for mathematical notation, but we can represent it by like an indicator value of like if this like H pre, that is this neuron over here, is greater than 0, then the output is 1. Otherwise, it's 0. It's basically saying the same as this right over here, but it's just more concise notation. So we're going to use this now in order to compute the gradients for each of these neurons. So let's see how to do that. So for this first neuron over here, this neuron's gradient is, well, how does this neuron affect this neuron times how this neuron affects the loss? Well, we know that how this neuron affects this neuron, since it's already like less than 0, then that means that, well, we write it in this way. The effect is going to be 0. So changing this neuron does not affect this neuron. So the value is going to be 0. Now, taking this neuron over here, how does this neuron affect this neuron times this neuron affecting the loss? Well, this is greater than 0, so it's going to be 1, right? It affects it with a 1, and that's kind of what we write over here. This is going to be 1. And how does this neuron affect the loss? Well, we computed it, 0.5488, and that's what we write over here. And so we write delta over here as 0.5488. And similarly, this last neuron, because it's lower than 0, changing this does not affect this neuron, and hence overall changing this does not affect the loss. And that's why we write 0, and hence we write the delta is equal to 0 right above that neuron. Now we have encountered another weights layer, W2, right? So we want to find the gradient of the loss with respect to this every single weight here. So let's just do, from the first neuron, right? We have this, and this, right? So let's just take this first neuron. How does changing this weight affect the loss? Well, it's how changing this weight affects this neuron times how changing the neuron here affects this loss. So we already know this is 0, so the effect is going to be 0. How does changing this weight affect the loss? Well, it's how changing that weight changes this neuron times how this neuron changes the loss. Well, how does this weight affect the neuron? Well, it's going to be what the input is. That's 0.6, right? Times how this neuron affects the loss, which is 0.5488. We do that math right over here, and we see that it's 0.3268, which we log over here. Now for this 1,3, that's this weight over here. How does this change the loss? Well, it's how it changes this neuron times how this neuron changes the loss. That second term is going to be 0, right? So that's why the overall value is just going to be 0, and we log it in the table as such. And we do a similar computation for each of these other weights coming from this second neuron here. And we're going to get 0, 0.8172, and 0 here. Next, we are now going to compute the gradients of each of these values in the P layer, its pooling layer, to this output. So how does changing this neuron affect the loss? Well, it can be in 3 ways this time. It's how changing this neuron affects this neuron times how this neuron affects the loss. That's this first term over here. Then it's how changing this neuron affects the second neuron times how this second neuron affects the loss. That's this term over here. Then how changing this neuron affects this third neuron, how this third neuron affects the loss. That's over here. And then, if you substitute the values that we've already computed and use the inputs, the weights as such, right, as multipliers, you're going to get negative 0.10896. That's what we write as the gradient over here. And it's very similar. In a very similar way, we compute the gradient here to be the positive of that value. And its computation is just given right over here. Next, we move on to this layer here, the C layer here. Now, there is like a pooling in between here, so we need to deal with this. So we have a max pooling, which is going to be the maximum of all of these values, is going to be this values activation here. Now, the derivative of this, well, it's, the derivative specifically of just, let's say, this neuron, right? So how does this neuron affect the loss? That's what we want to calculate. It's how this neuron affects this neuron times how this neuron affects the loss. We already have that second term. That's this negative 0.108 over here. But how does this neuron now affect this neuron? That is going to be given by this del P1 by del C term, right? And we can see here that, this is a max pooling case. So if the value is actually not maximum, as is the case for like this or this neuron, changing this by a little bit is not going to affect this output. So it's going to be 0. It's only going to change, though, if we change the value that is actually maximum, and it'll change by exactly how much that is. So in this specific case, it's going to be like this neuron, that's 1,1, as well as this neuron, which is in 1,3. They are maximum. And we'll just choose one of them just deterministically. Let's say the first neuron that we encounter that is the maximum becomes the maximum. And therefore, for this specific example, we're going to define our derivative as well. It's going to be like the derivative of this neuron with respect to this neuron is going to be 1. But for all other cases, changing these output activations is not going to change this output here. and hence it's 0. And now if we want to, I'm just going to like mathematically define the exact same thing. I'll use this indicator term right over here just to be like, okay, if like this ij term is like such that I is 1 and j is 1 for this specific case, then it's going to be 1. Otherwise, the output is 0. So let's now use this to compute the gradients for each of these neurons. So you can see here that to compute, let's say, this neuron gradient, right? It's this neuron times how it affects this, which is 1, times how this neuron affects the loss, which is negative 0.108. That's given by this first entire thing. If you do the math, it's just that value here. And the gradient of how each of these other neurons affects this neuron is just going to be 0 throughout. So hence, I've written them in like slightly lighter gray so that we don't need to be confused by them. And, I've written only like 3 computations here, but you can see that we would make 9 computations and write them over here. Hope that kind of makes sense. Next, we'll look at this layer of neurons over here. Well, in this case, it's even more easy to see that this is the maximum value here, right? So for this specific case, how does this neuron affect the loss is how this neuron affects this neuron times how this neuron affects the loss, right? So how this neuron affects this neuron, well, we're taking that in the form of this derivative. And because it's the maximum for this case is in position 1, 1, it is 1 if, we're talking about position 1, 1, but it's 0 for all of these other neurons. So changing them does not affect this output. And using them in our computations, we have now computed these deltas, right? And it's only this first neuron that actually has a 0.108 gradient value. Everything else is 0, which we've written in very light gray. Now let's actually make the computation for this layer. Once again, this is kind of just like a ReLU activation. So what we do here is how does this neuron affect the loss? It's how the same neuron affects specifically just this neuron, right? And times how this neuron affects the loss. And we know that how this neuron affects this neuron, because it's greater than 0, like we have seen here, we would compute this value in this way right over here and say that its value is just going to be negative 0.108. It's the same effect. And for each of these other neurons, because, changing each of these corresponding neurons does not change the loss, even changing these neurons will not change the loss. And you can kind of mathematically see how that's done right over here. And you can derive the calculations for the others, and you'll just get 0 for this specific case. Now, we do the exact same computation for this set of neurons here. So how does changing this first neuron affect the loss? It's how changing this neuron affects this neuron times how this neuron affects the loss. Now, because it's ReLU, it's going to be like a pass-through. So the derivative is just 1, right? Times whatever effect this is, 0.108. And that's why it has the same effect on the loss. And everything else has no effect on the loss. Now we come to the feature maps layer. So now what we want to do is, these are like shared weights. And we want to compute how does changing this shared weight affect the loss over here. Well, it's how affecting this shared weight affects each of these neurons over here, each of these 9 neurons. And why this is the case is because these are shared parameters. When you perform a convolution operation, you are sliding this over, windows over the input here, and they will be used to calculate each of these parameters here. So this specific parameter value affects each of these neurons over here. And so changing this, how does that affect the loss? Well, it's how changing this affects this neuron times how this neuron affects the loss. That's this first term over here. Plus how this change affects this neuron second here, and how this second neuron affects the loss. That's this term over here. Plus 9 terms total. and that's like how this neuron also affects this last neuron times how that affects the loss. That's over here. So this entire thing is going to be like 9 terms. And so we perform the computation. We already know like half of these terms just off the bat, right? And we know that, how does this neuron affect this neuron specifically? Well, it only affects it when the sliding window is right here. And at that point, what's being multiplied by this is this specific input 1 over here. And that's why you see like 1, 1 input here. And similarly, like how does this first neuron affect this second output here? Well, it's only when the sliding window is right over here. And specifically, it's going to be of this 1, 1 here, which is, hence it's like I, 1, 2, right? And that's why we can kind of like substitute them all the way. And if you substitute all the values, you're going to get negative 0.108. And we will store this in our 3x3 table of weights over here. Now that's for just this. Next, we'll compute it for this neuron here. Well, again, this neuron affects the loss is the sum of effects through each one of these neurons. That's exactly what we see right over here. Now, how this second feature parameter affects this first neuron is already when it is on this like initial part over here, and it's going to be multiplied by this 1. So that's where that 1, 2 is coming from. Similarly, how does this neuron affect this right over here? Well, it's going to be when the feature map is right here, and it's this one that's going to be affecting it, right? That's where 1, 3 is coming from. And if you substitute all of these values, you're going to get negative 0.108, which we write over here. And we do this for, next is like this third value over here, which again, so when we do this by hand, how does this neuron affect the loss? It's going to be how this neuron affects each of these neurons times how each of these 9 neurons affects the loss. That's this first line over here. Next, how does this third neuron, now how does it affect this first neuron? Well, it's when, the sliding windows over here, and this third neuron is going to be the multiplier for this neuron here, and that is the one that we see here. Similarly, how does this, let's say, how does this third neuron now affect this last neuron over here? Well, it's when this entire sliding window is on specifically this region over here, and the third neuron is going to be multiplied by this 1, and that's where we see 1, 3, 5. Third row, fifth column, right? And if we multiply the values along with all of these effects of gradients, you're going to get negative 0.108, which is exactly what you see here. Similarly, now in this next case, we want to see how changing this neuron at 2, 1 is going to affect the loss. It's how changing this neuron affects each and every single one of these times how each and every single one of these 9 neurons affect the loss. That's the first line, right? And specifically, how does this neuron affect this, let's say this first neuron over here? Well, it's when the sliding window is right over here, and that 2, 1, it's going to be like this multiple. This input is going to be that multiple, right? For this specific feature map. And that's what we see right over here. And similarly, how does this neuron affect this case? Well, it's going to be, when the feature map is right over in this last region over here, and we see 0 here, right? In the 2, 1 region for it, and that's exactly why we see 0 over here. And hence the overall value after you substitute these, for these 9 terms, we get negative 0.108, which you populate over here. Next in this, this case, which is how does this value affect the output loss? Well, it's how changing this affects each of these values times how changing each of these values affects the loss. Well, we know how changing this affects the first neuron here. Well, if we look at this over here, we know that the multiplier is going to be 0 for this feature map. That's why it's 0 times this, whatever we have the gradient over here. And because every other gradient is going to be 0, it doesn't really matter about all the other terms. They're going to be 0 anyways. And hence we get a value 0. And that's why we see 0 here instead of like negative 0.108. For a similar reason, we see that changing this neuron does not affect the loss as well. And we see that changing each of these, this neuron affects, how it affects the loss is by this value. And the same is for how changing this neuron changes the loss and how also this neuron changes the loss. So I hope all of that makes sense. Next, we do the similar kinds of computations for this convolution layer here. So how does changing this neuron affect the loss? Well, it's how changing this neuron affects each of these neurons times how each of these 9 neurons affects the loss itself, right? And how each of these 9 neurons, that effect is going to be capitalized right here in this statement. And, how does this neuron affect this first neuron over here? Well, it's given by the multiplier when, the feature map is on this region and specifically in the 1, 1 slot. So that's 1, which is exactly why we see this here. Doing the math, you get 0.108. And you can kind of see that for each of these cases, right? How does this affect the loss? It's how this affects each of these neurons times how each of these neurons affects the loss, which you'll get the same value. The same cases for this third neuron, this neuron in 1, 2. And now the neuron over here, right? How does this neuron affect the loss? It's going to be no effect on the loss. Again, it's mostly because how does this neuron, let's say, affect this first neuron here? Well, if we consider this region, subregion over here, it's going to be, the multiplier is just going to be this 2, 2 neuron, which is 0. That's why we see it here. All their terms are going to be 0 because the effects are also 0 here. And that's why we get a final output value of 0. Same is the case for this neuron here. And for each of these other subsequent neurons, how changing this neuron affects the loss is given by this value. And same for this neuron affecting the loss and this one too. And so effectively, we have now officially computed or determined how changing each weight affects the loss. That is how we have determined each of the gradient values that correspond to our gradient vector. And the idea, remember, to the beginning of the video is we computed this entire gradient vector to understand how to update our weights. Because now this gradient vector is going to give us the direction of steepest ascent. And so what we want to do is substitute it in our gradient descent update rule. It's descent because we have a negative sign, negative of steepest ascent. We let the learning rate be 1 for simplicity and calculation. And now let's actually compute the weight updates. So specifically, we'll do it from like forward to back, even though we computed the gradients in the reverse direction. It shouldn't matter since we're updating them all effectively at the same time. So to update this weight over here, so it's going to be W, which is 0.2, minus like the gradient, which is this value over here that we get from our table, negative 0.108. And doing that subtraction, you'll get negative 0.091. And similarly, we can do how, changing each of these weights over here in this like 3x3 grid, how they are going to update. They are given by values right over here. And we can just write them out individually here just to see like what they look like. Next, we do the same for these 3x3 grid of values. We take each of these values and subtract it by the values we computed in our table for the gradients for these same parameters. And so we would get these sets of values right over here. And, if we were to just plug these values directly into this figure, you get something that looks like this. Next, we have like this set of, 2x3 weights over here. So we take each of the values, that's weights W, and then subtract it by the corresponding table value here. And we're going to get these sets of values here. And we will update, whatever needs to be updated. In this case, it's only like 2 weights that are updated and the remaining remain the same. Next, for our last weight layer over here, we're going to take, again, the weight values subtracted by the corresponding gradients, and you can kind of see that only, again, 2 of these weights are updated. And so we have updated all of the weights right here, all simultaneously with just one backward pass. And this was like one iteration of the algorithm for one sample. So I hope this gives you a good understanding of how convolution neural networks actually compute gradients and update weights with this backpropagation algorithm, and hence how they learn. Now, in addition, I've also put together a sample piece of code that will create the convolution network with the same architecture and initializing even the same weights that I've seen here. And I've also printed out, what were the weights previously and what are like the new set of weights, right? And this can kind of just help us like verify like if we're doing everything correctly. And when I do that, I see the values that, for the weights that we see here, they are exactly as we have computed by hand. So overall, this gives like a good like gut check to show that the values that, we computed are correct. And I can probably share this code too, because it might be helpful to you. Quiz time. Have you been paying attention? Let's quiz you to find out. Why does the gradient descent of a feature map parameter in a convolution network have many terms during backpropagation? A, each output neuron is computed from a different set of weights. B, the same feature map parameter is reused across the input image. C, the gradient needs to be averaged across all layers. Or D, each weight only affects a single output, so we sum over the time steps. I'll give you some time to think about this. The correct option is B, but can you tell me why? Comment your reasoning down below and let's have a discussion. And at this point, if you think I deserve it and you love what you're seeing, please do consider giving this video a like because it will help me out a lot. And that's going to do it for quiz time, but before we go, let's generate a summary. So in this video, we took a look at what and why backpropagation. And then for a sample convolution neural network that kind of looks like a Linnet architecture from the 80s and 90s, and we took a simplified version of that, we computed the forward pass at first, a high level, and then a backward pass as well, right? And hopefully all of these computations and calculations make sense because we use these then to update the weight parameters from the network simultaneously. And we also took a look at some code that also helps us verify that these values are largely correct. So I'm going to share some resources, this video, along with like some slides too, down in the description below. So do check that out. And like I said before, I think you'll learn the most from this entire process by doing it yourself by hand and kind of using this video as a resource to get general guidance and also check your work and also just show you that this backpropagation algorithm entirely is not something that's so arcane that you can't understand it. Because clearly we can do the mechanics and at least compute it by hand. So that's all I have for today. Please consider liking and subscribing to this video if you think I do deserve it, and I will see you in the next one. Bye-bye.